You know, some of the scariest looking symbols in math, they aren't actually there to make things harder. Nope, they're actually shortcuts. And today, we're going to pull back the curtain on one of the most elegant shortcuts I've ever seen. And we'll do it by starting with a really simple question.
So here it is. How would you go about adding up all the numbers from 1 all the way to 100? I mean, sure, you could grab a calculator and just start punching in numbers, 1 plus 2 plus 3. But man, that would be incredibly tedious, wouldn't it?
Yeah, you could totally do it that way. 1 plus 2 is 3, plus 3 is 6, plus 4 is 10. But you would be here for a long time. But it turns out there's a much more beautiful, a much more elegant way to solve this. It's a trick so clever, it almost feels like a secret handshake among mathematicians.
Okay, so to get to that secret handshake, we first need to make sure we're all speaking the same language. We've got to learn the language of patterns, and that starts with 2 really important words that sound kind of similar, but trust me, they mean very different things: sequence and series.
So a sequence is really just a list of numbers. That's it. It's a list where the numbers are arranged in a specific order based on some kind of rule. Like, for example, 2, 4, 6, 8. That's a sequence. The rule is just add 2 to the last number. See? Simple as that. It's just an ordered list.
A series, on the other hand, is what you get when you actually add up all the numbers in a sequence. So if we take our last example, the sequence 2, 4, 6, 8, well, the series would be 2 plus 4 plus 6 plus 8. A series isn't the list, it's the sum of the list.
All right, let's put them side by side so you can really see the difference. Over on the left, you've got the sequence. It's just a list, separated by commas. The order really matters. But on the right, you've got the series. It's a sum, separated by plus signs. That's probably the easiest way to remember it. Commas for a list, plus signs for a sum. A sequence is the list, this series is the sum of that list. Got it? Cool.
Okay, so if a series is a sum, and some of these sums can get, incredibly long, like our 1 to 100 problem, how on earth do mathematicians write them down without using a mile of paper? Well, they use this guy. Now, I know it might look a little intimidating, but it's really just a super powerful piece of shorthand.
This big E-looking thing is the Greek letter sigma. It's basically their S, which is perfect because it stands for sum. I love thinking of it like a recipe for addition. It tells you exactly what to do. The number at the bottom, that's your starting ingredient. It says, hey, start counting at this number. The number at the top is your stop sign. It tells you where the recipe ends. And that little formula on the right, that's the main instruction. It's what you actually do with each number as you count up.
Let's walk through the steps. It's actually really simple. First, you take that starting number from the bottom and plug it into the formula. Boom, you've got your first term. Next, you go up by 1. So if you started at 1, you're now at 2. Plug that into the formula and add the result to what you had before. And you just keep doing that, counting up by 1, plugging it in, and adding it to the pile until you finally hit that number at the top. That's your last step. You're done. It's literally a summing machine.
All right, so we've got our vocabulary down, sequence versus series, and we've decoded the mathematician's shorthand, sigma. Now it is time to put it all together. Let's go back to our original problem, adding up 1 to 100, and finally reveal that incredible shortcut.
Now, a series like 1 plus 2 plus 3 plus 4 and so on, it actually has a special name. It's called an arithmetic series. That's just a fancy way of saying you're adding the same amount each time. In our case, we're always just adding 1. And the really cool part? The trick we're about to learn works for any arithmetic series, not just this one.
Okay, let's zoom out for a second and think about this in general terms. We'll call our total sum S. We can write it out, right? You start with the first term, we'll call it A sub 1. For our problem, that's just the number 1. The next term is just that first term plus whatever we're adding each time, which we'll call D. Again, for us, D is also 1. And you just keep doing that all the way up to the very last term, A sub n, which for us would be 100.
But here comes the aha moment. This is the clever part. We all know that the order you add numbers in doesn't matter, right? Like 2 plus 5 is the same as 5 plus 2. So, what happens if we write down our exact same sum, but we write it backward? We'll start with the very last term and count all the way back down to the first.
Okay, now look what happens when we stack these two on top of each other and add them straight down. On the left side, S plus S, that's easy. It's just 2S. But look at the right side. This is where the magic happens. The first column is just the first term plus the last term. But now look at the second column. The plus D and the minus D perfectly cancel each other out. And what are we left with? The first term plus the last term, again. And this happens for every single pair all the way down the line. It's beautiful.
So here's the bottom line. If we have n numbers in our list, that means we have n of these pairs, and every single pair adds up to the exact same thing, the first number plus the last number. We just turned a giant messy addition problem into one simple, clean multiplication. 2 times our sum is just n times the first plus the last.
And of course, we just want our original sum, s, not 2 times s, so all we have to do is divide by 2. And there it is. That's the formula. That is our elegant shortcut. You just take the number of terms you have, multiply it by the first term plus the last term, and then divide the whole thing by 2. So let's finally answer our question from the beginning. How many numbers are we adding? N is 100. What's the first number? A sub 1 is 1. And the last number? A sub n is 100. So we plug it in. 100 times 1 plus 100, all divided by 2. That gives us 50/50. And that's it. No calculator mashing, no long addition, just one beautiful, simple calculation.
Now, this trick is awesome, but believe it or not, it's really just scratching the surface. These ideas, sequences, and series, they open up this entire world of mathematics, a world that even lets us start to wrestle with a totally mind-bending concept, infinity.
I mean, think about it. What if, instead of adding the same number over and over, you were multiplying by the same number? You know, like 1, then 2, then 4, then 8. Well, that's called a geometric series. And yep, you guessed it, they have their own set of incredibly cool shortcuts too. And this is where things get really, really wild. What if a series never stops? What if it goes on forever? You'd think an infinite sum would have to equal infinity, right? Well, not always. Just look at this. If we take a square and we add up these areas, a half plus a quarter plus an eighth plus a 16th, and we do that forever, we are adding up an infinite number of pieces. But look, they perfectly fill up that one single square. The infinite sum is just 1. How cool is that?
And really, that's the big idea here today. Math isn't just about plugging numbers into a calculator. It's about something much deeper. It's about finding the hidden pattern in a problem and then creating a beautiful, powerful tool, like that sigma symbol or our slick new formula, to handle it with total elegance.
So I'll leave you with this final thought. We just took a problem that looks super tedious and complicated, and we found a stunningly simple shortcut hiding inside it. It really makes you wonder, doesn't it? What other complex-looking patterns out there in the world are just waiting for someone to find their own elegant shortcut?